got here is the Clausius-Clapeyron equation. That's at the top here. And the other important definition we need is what boiling point is, and that's boiling temperature at atmospheric pressure. And this is something you actually do obtain. So what we're going to do here is let's assume that we see a boiling point of, let's say 97 degrees Celsius, and the atmospheric pressure which we get off a barometer in the lab room is going to be, let's say, I'm going to say 748 millimeters mercury. This can vary. It's not always 760. We assume that 1 atmosphere is 760, but in reality, air pressures vary all the time. Now what we're interested in here is solving for, in this case, P2. And we're looking for P2 at T2, which is 295 Kelvin. Now this is something we're told in the lab, that we want to just figure out what that vapor pressure is at 295 K, which is pretty close to room temperature. We're talking about 22 degrees or so there, 22 degrees Celsius, but 295 K. And the other thing we're going to do is convert this 97 degrees into kelvins as well. We need that. This is going to be our T1. So our T1 is going to be this in kelvins, so you can work that out. And P1, we can leave it as millimeters of mercury, and that will allow us to calculate P2. Will have the same unit, it'll be millimeters of mercury. The unit of P doesn't really matter that much. It could be millimeters of mercury or it could be atmospheres, but it's not going to make any difference because whatever you end up using here will be the same unit as you get for P2 anyway. So if we've got this as our variables here, then effectively here's what we're doing. We've got log P2 over 748 millimeters of mercury and that equals delta H vap over R, and then we've got to figure out what delta H vap is. Now we can do that because we're given a bit of information here. This is the Clausius-Clapeyron equation, which you can get from your lab manual. But the other piece of information we can get is delta H vap, and we can do that using this possible liquid unknowns chart. Your unknown is going to be one of these. Now I'm saying that the boiling point was 97 degrees, which would point us to 1 propanol here being the unknown in this case. And that means we can actually just read the heat of vaporization off the chart here, and you can see it's kilojoules per mole. Now the R value that you're going to use is going to be 8.314 joules per Kelvin, joules per mole per Kelvin. And that's going to be important as well for the units. But let's go back here and get the delta H vap, and you can see that it's going to be 47.5 kilojoules per mole. And that's over the R value, which we said was 8.314, but it's joules per mole per Kelvin. So as you can see, the issue we're facing here is that these kilojoules and the joules don't cancel. So what I'm going to have to do is do a conversion here of 1000 joules to kilojoules, and that will get rid of the kilojoules, leave me with joules. And you can see that whatever we get here is going to have the unit of K once it goes on to the top here, which is good because this comes out to be 1 over K, which means the K's cancel and we end up with no unit, which matches what we have because a natural log of something shouldn't have units anyway. So at least you have for this equation here. And now we've got 1 over 295K minus 1 over whatever 97 degrees is in Kelvin. So whatever you get here, that will go over here. So we're going to end up with a number here that we can use, and then we have to isolate P2. So what we can do there is we'll have, and I'm just going to call this number X, for now, whatever this comes out to be. I'm going to get you to figure that out. So we've got ln of P2 over 748 millimeters of mercury is equal to x, so ln of P2 over that. So now we've got to isolate the P2. Now what we can do here is we can do the inverse log of both sides, natural log of both sides, which would be e to the power of. So we end up looking at something like this. P2 equals 748 millimeters of mercury equals e to whatever we got for x there. And we can do that in the calculator looking at the inverse natural log button, the inverse ln, or the second function ln button. Then you can see that getting P2 is pretty easy. We just multiply both sides by 748 millimeters of mercury, and that will lead us to our P2 value.